This video is on quadratic functions. We'll start with the definition of a quadratic function. A quadratic function is a function that can be written in the form y equals ax squared plus bx plus c, where a is not equal to 0 and a, b, and c are all real numbers. Remember, this is our symbol for the set of real numbers. So when a quadratic function is written in this form, we say that it is in standard form, although it is still a quadratic function if it is written in some other form. Frequently, quadratic functions are useful to look at when they're factored out, or, well, there's one more particularly useful form of a quadratic function, which we'll get to in a second. Some interesting facts here. Every quadratic function is also a polynomial function. You can compare the definition that we just had of quadratic functions to the definition of a polynomial function, and a quadratic function is always a polynomial function of degree 2. Every quadratic function has a parabola as its graph. And every quadratic function is a transformation of the square function. And that square function, remember, is the function y equals x squared. So you can get any quadratic function, anything that is possible to be written in the form ax squared plus bx plus c, by transforming the square function, by stretching or flipping or shifting from up and down or side to side. Some combination of those can get you every single quadratic function that exists. And because of that, if you remember our function transformation rules, every quadratic function can be written in the form y equals a times x minus h squared plus k. And this is called a vertex form. Vertex form of a quadratic function is extremely useful, as we will see. There you have it. Vertex form is useful. So let's consider the function y equals negative 2 x minus 3 squared plus 5. So the vertex of this parabola is then shifted to the right 3 and up 5. So the vertex of the square function is at 0, 0. The vertex of this parabola is at 3, 5. This, incidentally, is why we call this form vertex form, because you can tell just at a glance where the vertex is. We haven't addressed this negative 2 yet. It opens down. I know that because this is a negative. And remember, having a negative multiplied in front of your output here, that reflects over the x-axis. That means my parabola opens down, and it has been stretched vertically by a factor of 2. So the negative tells me which way it opens. The fact that it's a 2 tells me how much it's been stretched. Remember, if this is less than 1, it's been shrunk instead of stretched. That is from our module on function transformations. So with that information, we can draw a little sketch here. I know that my vertex is at 3, 5, so my vertex will be about here. And my parabola will open down, and it's sort of stretched out. So ordinarily, since this is was arrived at by the square function, you could move over 1 and move down 1, move over 2, you would move down 4. To sketch this, when you move over from the vertex 1, you would move down 2 since it's been stretched. When you move over 2, you square that and then multiply by 2 because of this, and you'd move down 8. Let's actually see that graph. And there is the graph. Now, I'll refer to this graph, but notice for the rest of this, it's not actually necessary to have the graph in front of you to answer the questions, although you are always free to draw a graph if you think it might help you. The axis of symmetry is x equals 3. Notice that every parabola has an axis of symmetry where it is the same on the left and the right side of this vertical line. For this particular parabola, that vertical line is x equals 3. It is always going to go through the vertex, so you can really just look at the x-coordinate of the vertex to find the axis of symmetry. Next, I want to point out it is increasing on the interval -infinity to 3. And sometimes it throws people because this arrow is pointing down. But whenever we talk about increasing or decreasing, we always read from left to right. So as I go from left to right, this function is going up, which means it is increasing until 3. And this interval, incidentally, is an interval of the domain. When we talk about where a function is increasing or decreasing, I'm always going to be interested in what part of the domain is it increasing or decreasing on. So what x values is it increasing and decreasing for? And it is increasing from -infinity to 3. Then after 3, from 3 to infinity, it's decreasing. A parabola has exactly one turning point. It's not going to turn around and start increasing somewhere else, although other polynomial functions might do that. A quadratic function never will. It has a maximum point of 3, 5, which incidentally is the vertex. Every parabola will have either a maximum point or a minimum point. It will always be the vertex. If the parabola opens down, as this one does, it has a maximum point. If you had some other parabola that opened up, you would have a minimum point. And if I talk about the maximum value, what I'm interested in is the y-coordinate. So the maximum value of this function is 5. Finally, the domain and range of this function. Well, the domain of any quadratic function is going to be -infinity to infinity, all real numbers. Incidentally, that is the domain of any polynomial function as well. But more specifically, it is the domain of this particular function that I've got right here. And its range is -infinity to 5. A quadratic function will only have one infinite endpoint on its range. It will either go down forever or up forever, but not both. In this case, it goes down forever, so it goes to -infinity, sort of begins from -infinity, and then at 5 is, 5 is the highest y-coordinate. That's the maximum value. Notice that I do use the square bracket because 5 is part of the range. There is a point on this function that has a y-coordinate of 5. And that point, incidentally, is the vertex. So vertex form is very useful. You can get all of this information directly from just looking at the function in vertex form and knowing how to interpret it. So now, let's have another example. I've got the function y equals 1/2 times x plus 4 squared minus 1. And we'll have this as a fill-in-the-blank exercise. At this point, you should pause the video and answer all of these questions, and then we will go over the answers together. All right, so let's go over these answers. I've got this function here, y equals 1/2 x plus 4 squared minus 1. The vertex of this parabola, remember vertex form is x minus h, so I always take the opposite of this value for h, my x-coordinate of my vertex, is -4, and my k is -1. So the vertex of this parabola is -4, -1. The number that is in front here is positive, so it opens up. And since it is less than 1, it has been shrunk vertically by a factor of 1/2. Its axis of symmetry, oh wait, actually I think I have the sketch of the graph next. That's what that graph looks like. Its axis of symmetry is, you always use the x-coordinate of the vertex. So its axis of symmetry is x equals -4. Now it is here it's decreasing. It is increasing from -4 to infinity. And it is decreasing from infinity to negative infinity to -4. Remember, these intervals are always what intervals of the domain. Now, each parabola has either a maximum or a minimum point. This parabola opens up, so it has a minimum point. That minimum point is the vertex, which is -4, -1. And so it has a minimum value of -1. My negative's a little short there, but it's still a -1. Its domain is -infinity to infinity, as it is for every quadratic function. And its range, notice since it has a minimum value, it has a lowest y-coordinate, so that's -1 to infinity. And that concludes this video. Next, you will want to watch the video on how to put a function into vertex form. We know it's useful, so now we need to know how to do it.